one, I have question 21 from chapter 9 asking which ketone will show a carbonyl absorption at the lowest frequency in its IR spectrum. Let's just compare our solutions we're given, and we have everything looks like the same molecule except D, more or less, because D has an extra methane on top, and every bond carries more energy. So if this has a whole 4 atoms attached, that's more energy, so that would definitely not be the lowest. The more energy required, the higher the frequency will show on the IR spectrum, so we can cancel out D. Now A looks similar to B and C, but it doesn't have an alkene, meaning that there's a proton there attached, so that's still requiring more energy than the double bonds. Now double bonds, they have more energy than one single bond alone compared to two single bonds, but less than two single bonds. And now we have two alkenes connected to a carbonyl here. Now double bonds, I'm sorry if you heard that. Double bonds, while they do carry more energy, that's because when you have two bonds connected, it takes a lot more energy to stretch the C and the O apart, or stretch the two atoms apart. So the way you would take less energy is if you do resonance and you cancel out the double bond, or you limit the double bonds. So let's say if we did resonance to this one here, we could put this double bond over here, and this one can't go over there because then this would be a Texas carbon. So we would put this double bond over here. So when we redraw it, it would look like this, which it still seems about equivalent to like how it was previously. Let's redraw B, where we do resonance over here, and we could also do the resonance over there as well. Now we've reduced the amount of double bonds present, so this will require the least amount of energy, meaning that it'll be the lowest frequency. So B has lower energy than C, which is why B is our answer. The second question I have is question 9 from chapter 10 asking what is the major product of this reaction, and it has a butene reacting with a HBr and peroxide. So usually if the peroxide wasn't there, we'd be doing a regular Markovnikov addition where the alkene would attach to the hydrogen, and then the hydrogen will go to the less substituted side, then the Br would attach to the more substituted side. But because we have peroxide in the mix, peroxide will actually generate a bromine radical, and so this radical really wants to bond with something else, and the alkene is here, but to stabilize it as much as possible, the bromine will attach to the less substituted side over here, which would then result into one. Oh my gosh, that's ugly. Br here, and then the radical being on the other end. And then this radical here will then pull off a proton from another HBr here, which is feeling acidic because it's connected to a bromine. And then it'll be satisfied. Therefore, our answer... Hold up. Okay, I cut off a couple, that's why. There we go. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Therefore, our answer is D. Again, it wouldn't be any of these because it's not doing Markovnikov because peroxide is present.